In a previous chapter, we learned about complex ions. Transition metals tend to form complex ions. And here we have a central metal ion that has one or more ligands bound to it, and as a whole, this has a charge. So this is not a compound between cobalt and ammonia. The ammonias are bound to the cobalt, and overall this is an ion, and so then as a compound, it needs to have anions as well, counterions. A counterion is an ion that's the opposite charge and makes up the difference in charge. So coordination compound is a neutral compound consisting of a complex ion and one or more counterions. There are two types of interactions that metal ion has. One is the primary valence, and so that's the oxidation state on the central metal ion. And then we also have the secondary valence, more commonly referred to as the coordination number, and that's the number of molecules or ions bound directly to the metal. So the number of ligands. So as an example, CONH3 6 Cl2. Here we have cobalt, and it has 6 ammonias bound to it, right? And then there's counterions here. So what's the primary valence on that cobalt ion? What's the oxidation state on the cobalt? It's going to be the charge on that metal ion, right? So any ionic compound, you can pull it apart into cations and anions, right? And so this guy would be, let's put it up here. We've got cobalt, NH3 6, and we've got Cl minus. We have 3 of these, right? Cl3. So what's the charge on that guy? +3. So at this point, I'm imagining that if I ask you, do you have any questions, nobody's going to say anything because your mind is like full of things you don't understand, but you can't put them into words. Is that about right? It's like, yeah, but I can't form any questions because that's how lost I am. That's okay. So a complex ion, that's the metal ion with its ligands, is a Lewis acid-base adduct. Remember, in Lewis acids and bases, we have electron pairs that are being donated, right? So here we have a silver ion, and it has no valence electrons. And a Lewis base, like ammonia, each nitrogen has a lone pair. And so it can form a coordinate covalent bond. The nitrogen can share its lone pair with silver to form a covalent bond. So this is a covalent bond between silver and the nitrogen. But both of those electrons come from the nitrogen. And then here's another ammonia. The nitrogen has a lone pair, and so it's sharing a lone pair with silver. So these are coordinate covalent bonds where both electrons come from one atom. It's being extra generous. The Lewis bases are the electron pair donors. And so ligands are good Lewis bases. Ligands, we'll see, are going to have at least one lone pair, and that's how they form a bond with the transition metal ion. This is called a Lewis acid-base adduct because it's a Lewis acid and a Lewis base together. So here's a table from your textbook showing some common ligands. There are other ligands, but for the most part, these are the only ones we're going to look at. If we look at the Lewis structures for these guys, we see that all of these have lone pairs, right? Here, the oxygen has 2 lone pairs, nitrogen, chlorine, everybody has lone pairs. So water, ammonia, chloride ion, carbon monoxide, there's another molecule. The cyanide ion, there's a polyatomic ion, thiocyanate ion. So this is one that shows up in our qual scheme for our lab practical. You add potassium thiocyanate, and it forms a complex ion with the iron. Remember what color that was? Red. It's like blood, right? It's like really, really red. You can't see through it. It's actually almost creepy. But it's not thick like blood. The oxalate ion. We've talked about oxalate compounds before, oxalic acid. Here's the oxalate ion as a ligand. So this, being kind of a long name, is given an abbreviation OX. This is ethylene diamine, which is abbreviated EN. And so diamine, this has 2 ammonias in it. And then this is ethylene diamine tetraacetate, or EDTA. And if you read labels on food and different things, you may see EDTA. This is a very common substance. So here we've got our diamine, right? Our 2 nitrogens, just like in this one, ethylene diamine. And then each of these has an acetate bound to it. And so we get multiple lone pairs that can form Lewis acid-based adducts here. So we can get the lone pair from these negatively charged oxygens and also the lone pairs from the nitrogens. So a monodentate ligand donates 1 pair of electrons. So dentate, we're talking about pair of electrons, 1 pair of electrons. And so water, ammonia, chloride, that would be monodentate, just 1 pair of electrons. A bidentate ligand donates 2 pairs of electrons. And those electron pairs are from 2 different atoms. So here's ethylene diamine, and we have a lone pair on this nitrogen and a lone pair at the other end of this nitrogen. And these lone pairs can bond with the same metal ion at the same time. So it can attach in 2 places. So bidentate. So ethylene diamine, this guy, and also oxalate can do that. So here's the structure of oxalate, right? And you can see this oxygen has a -1 charge, and this oxygen has a this one has a -1 charge. And so both of these guys can form a coordinate covalent bond with the metal ion. Polydentate, poly is just meaning more than 2. They can donate more than 2 pairs. And again, each pair of electrons has to come from a different atom. You can't have 2 pairs from the same atom. And so the only example we're going to see here is ethylene diamine tetraacetate. And that can do 4, or it can actually do up to 6. So the EDTA will wrap itself around the metal ion, and it can donate up to 6 electron pairs. So this is hexadentate, 6 pairs. So here we have cobalt EDTA. So we've got 1 cobalt in the middle, and we have 1 EDTA ion wrapped around it, and it's coordinating in 6 places. We got 1 up here, and then these 4 guys here, and that one underneath. Here we've got cobalt interacting with 3 ethylene diamines. And so each ethylene diamine is a bidentate ligand. It has 2 attachments to the cobalt ion. So there's 1 and 2 and 3. These sorts of complex ions have a special name. They're called chelates. They contain bidentate or polydentate ligands. And those ligands are called chelating agents. Any questions? Coordination number is how many attachments there are to that transition metal. So we can have coordination numbers from 2 up to 12. 4 and 6 are the most common. We'll see a coordination number of 2 with +1 ions. For all the first row transition metals, it's going to be 6 or less. Odd numbers are possible, but they're rare. The geometry of that structure is going to depend on the coordination number, but it also depends on the number of d electrons in the metal ion. So here we have some examples. Coordination number of 2, we've got 1 ligand on each side of the central atom, and so that's going to have a linear shape. We could have a square planar coordination with 4 ligands, and so we have 4 ligands in a square planar shape, or we could have a tetrahedral shape. So what's the difference between these two? It's a difference in the number of d electrons. That's what's going to cause it to be square planar or tetrahedral. If there are a coordination number of 6, that's going to take a octahedral shape. And so these shapes are the same ones we learned in VSEPR theory. If you have 2 electron groups, you're going to have a linear. If you have 4 electron groups, you're going to have tetrahedral. 4 electron groups, no lone pairs. Square planar would be 6 electron groups, 4 bonds, and 2 lone pairs. And 6 electron groups would be octahedral. So those should be a little bit familiar. We're going to learn how to name these guys. So there's a set of general rules, and this was originally proposed by a guy named Werner. So we're going to follow the general convention of, with the salts, these are going to be ionic compounds, salts. So you name the cation first, and then you name the anion. So here are the rules for naming complex ions. Name the ligands. Name neutral ligands as molecules. These are exceptions. So instead of calling H2O water, it's called aqua. NH3 is called amine, 2 M's. And CO is carbonyl. Anionic ligands have the name of the ion plus an ending that's modified. So if you have chloride, the "ide" becomes O, and that becomes chloro. If you have an ion that ends in "ate," like sulfate, that becomes sulfato. And if it ends in "ite," like sulfite, it becomes sulfito. So basically, for these "ates" and "ites, you're taking off the E and putting on an O. And back in table 26.4, we've got the names of some common ligands. Is that back or forward? No, it's forward. Okay, so here are some common ligands. So these are following that pattern. Bromide becomes bromo. Chloride becomes chloro. Hydroxide is hydroxo. Cyanide, cyano. Nitrite, nitro. Oxalate, oxalato. And ethylene diamine tetraaceto, acetato. Yeah. The neutral molecules, water, ammonia, and carbon monoxide have special names. So we've got to watch out for those. Oops. So we name the ligands, and then we're going to list the ligands in alphabetical order before the name of the metal cation. So amine would be listed before chloro, and chloro would be before nitrito, just going in alphabetical order. You know, because you have, what they want is there to be one best name for everything. Each thing has one best name that we're all going to come to, right? Some of them have some other names that people call them, more like nicknames, but there's like one formal best name for each compound. And so we have to decide on, well, what order are we going to put these ligands in? They decided alphabetical order. Okay, you can go with that. We're going to use a prefix to indicate how many ligands there are if there's more than one. So this is a little bit like naming molecular compounds. If there are two of them, di, 3, tri, 4, tetra, penta, hexa. So those are the same numerical prefixes we used for naming molecular compounds. If the name of the ligand already has a prefix, so like ethylene diamine, right, it's got a prefix di in it, then you're going to put parentheses around that, and you're going to use an alternate prefix. Instead of di, you're going to use bis. For 3, it's tris, and 4 is tetrakis. The prefixes do not affect the order. You put them in order by their name. So, examples, if we have something that says trichloro, that has 3 chloride ligands. Tetraamine means 4 amines, 4 ammonias. Tris ethylene diamine, so the tris is on the outside and there's parentheses here because there's a numerical prefix in the name of the ligand itself. So tris, 3 of the things in parentheses. So we name all the ligands, specify how many they are, got them in alphabetical order, then we name the metal. So if the complex ion is a cation, we just use the name of the metal, followed by the oxidation state written with a Roman numeral. So just like writing ionic compound formulas, right? CO3 plus, cobalt 3. PT2 plus, platinum 2. We can have complex ions that are anions. And so the names for these need to be different than the names for the cations. So here we're going to drop the ending of the metal and add 8. Remember, we used 8 for polyatomic oxyanions, right? Sulfate is a negative ion. So here we're going to take cobalt and change the ending to 8, cobaltate. Platinum becomes platinate. Copper, I guess copperate just didn't sound very good. So they go back to the Latin name cuprum, and so it's cuprate. But again, the charge, the oxidation state is in Roman numerals. Over here, we have some of the common metals and what they would be named as anions. So some of these you should be able to get just from the name, cobalt, okay, cobaltate. Gold is not goldate, it's aurate. And again, that's from the Latin aurum. Iron is ferrate. And so we use some of the Latin names here. Tin is stannum, and so in an anion, it's stannate. So the good news is you're not going to have a regular midterm exam on this topic, on this chapter, right? You're going to have a group take-home exam. 4 questions. And some of the question might be a little tricky, but you can look at your lecture notes and you can look at your book, okay? Because I don't expect you to remember all of this stuff, right? I want you to be familiar with it enough that if you see the name of a complex ion, you would recognize that that's a complex ion. If you needed to write the formula, you might have to refer to the rules. Or if you see a formula and need to write the name, I don't expect you to do that out of your head, okay? So that's a little bit of good news. And so then we put all those pieces together. We've got the ligands and the metal together. So examples here, PT NH32Cl4, 2-. So we have amine and chloro. Amine comes first in the alphabet. There is 2 of them. So that's diamine. There's 4 chlorines. Chloride becomes chloro. Tetrachloro. This is a negative ion. So platinum is then platinate, chloroplatinate. And then how do we know what the oxidation number is? So we have 4 chlorines, right? So that's a total of -4. And then we've got -2 here. So what does the platinum have to be? +2. So you look at the charges, the overall charge and the charge on any of the ligands, and that's how you figure it out. CONH36. Okay, this only has 1 ligand. NH3 is amine. There's 6 of them. Hexaamine. This is a positive ion, so cobalt and the charge. Well, NH3 doesn't have a charge, so all of the 3+ comes from cobalt. So hexaamine cobalt 3. Isn't that fun? Tremendous fun. So these tables might be useful in doing homework or that exam. So that's how you write the formula for a complex ion. How do you write a coordination compound formula? Well, you're going to have the complex ion and then the cation. Well, you form the cation and then the anion. For the compound. So this is review of what we just talked about. For the complex ion, you're going to write, back that up. We're talking about writing formulas now instead of names. Sorry, brain fart. So writing the formula, you're going to identify the metal in there first. That's going to be at the end of the name. And then you're going to write down the neutral molecules that are ligands, and then the anions that are ligands. If you have more than one neutral molecule or anion as a ligand, you're going to put them in alphabetical order based on the chemical symbol. So in the name, it's alphabetical order by name, and in a formula, it's alphabetical order by symbol. Okay, so let's do a little practice here. Name the following compounds. So there's 2 ions in a compound, a cation and an anion, right? And so the complex ion will be in brackets, which makes it much easier to see what it is, and then we'll have another ion. So here we have MnCO NH3,5, and we have SO4. And what's the charge on sulfate? 2-. So we have one of each of these, So if this is 2 minus, this one must be 2 plus. So we're going to name the cation first. And this is a complex ion. So we're going to look at the ligands. So CO is carbonyl. And NH3 is amine. Like ammonia, it has 2 M's. We're going to put those in alphabetical order. So the amine's going to go first, and then the carbonyl. So how many amines do we have? 5. So the prefix for 5 is penta. Penta, amine. And how many of the COs? 1. So we're not going to use a prefix, because if it wasn't 1, if it was a different number, we'd use a prefix. So this is another example of chemists not using the number 1. Carbonyl. And then the metal is manganese. And we need a Roman numeral here. Do these ligands have charges? This is carbon monoxide, neutral molecule. This is ammonia, neutral molecule. So this +2 charge must all come from the manganese. So this is manganese 2. And then the name of the anion, sulfate. So ionic compounds. Yeah, so compounds are going to have 2 names. Ionic compounds have 2 names, the cation and the anion. So this is the name of the cation. It's really long. It's all together, no spaces. And then there's a space that tells us, okay, that's the end of the cation, and this is the anion. If you had 2 sulfates here, you would not put a prefix, because we don't use prefixes that way in ionic compounds. We don't need them because the charges tell us how many there are. So any questions about that one? Okay, let's do this one. So let's look at what are the 2 ions that we have. Well, we've got sodium, and we've got PtCl4. Is the formula for sodium Na2? No. Sodium is just sodium. This 2 means that there's 2 of them. Right? What's the charge on a sodium ion? +1. So we've got 2 sodium ions. I'm going to have to replace the tip on my pencil. It is been dropped 1 too many times. So what's the charge on this complex ion then? Must be 2 minus. What's the name of this ion? Na plus. It's just sodium, right? Sodium. And then we name the anion the complex ion. So we start with the ligands. This is chloride. What do we call that? Chloro. And how many? 4. So this is going to be tetrachloro. And this is an anion. So instead of saying platinum, it's going to be platinate. Platinate. And you can just go back to this table and look at it. Okay, so platinum becomes platinate when it's an anion. It still needs a Roman numeral though. So we're going to look at what's going on inside here. we've got 4 chlorides, right? So that's 4 times -1. So -4 there. And we want an overall charge of -2. So what's the platinum? Must be +2. So that's sodium tetrachloroplatinate 2. Any questions? Yep, that's the end.